When a web application accepts user input without checking it first, the security of the entire underlying database is at risk. A single, carefully crafted string of text can apply enough pressure to the application's logic until it completely bursts open. In this session, we are targeting 3 specific vulnerabilities. We will manipulate database privileges, extract hidden records using a string-based injection, and bypass authentication using a numeric injection. Before we start, make sure your local webgoat application is running. We are picking up right at Lesson 5, SQL Injection Intro. Building secure architecture requires understanding exactly how an attacker dismantles it. We need to actively exploit these flaws to see exactly where the defenses fail. Step 1 takes us into Data Control Language, or DCL. Databases use DCL to manage who gets to do what, granting and revoking privileges that determine which users can view, modify, or delete specific tables. Our goal here is to elevate permissions for an unauthorized user group. Go ahead and enter the command grant alter table to unauthorized user. This syntax tells the database to let that specific group make structural changes. Click Submit, and a congratulations message appears. This confirms our payload was executed by the database engine exactly as written, permanently modifying its internal access controls. By successfully executing a DCL command through an input field, we have shifted from a standard user role to one with structural control. The database now treats the unauthorized group as having the authority to redefine the tables themselves. This diagram illustrates the mechanics of a Boolean logic bypass. The goal is to manipulate the query so it always returns a true result. Pay close attention to this highlighted section at the end, or 1 equals 1. The attack relies on that first single quote. When injected into an input field, it acts as a termination command. It drops in and cuts off the developer's original search parameter, isolating the name Smith from the rest of our payload. With the original query closed, the database moves to our injected condition, or 1 equals 1. Since the condition is always met, the database returns a result for every single row in the table, ignoring the original name filter entirely. By mastering this specific syntax manipulation, we can turn a simple search box into an open doorway for mass data extraction. Now let's apply this in Lesson 9. First, establish the expected application behavior. If we type a common name like John into the search box and click Get Account Info, the system returns a standard No Results Match message. Now we replace that normal search term with our payload. Type Smith, followed by a single quote, then or 1 equals 1. We are feeding the Boolean logic bypass directly into the text field. This image shows the immediate result. The blank search page on the left is replaced by a massive data dump on the right. User IDs, full names, raw credit card numbers, and active session cookies are all suddenly exposed. Precision is critical here. If you forget to include that first single quote, the database won't interpret your input as a new command. It will simply read it as a long, incorrect name, and the query will crash without returning data. Exposing every credit card in the system required 0 advanced tools. It only required a developer trusting a string input without sanitizing the characters inside it. Lesson 10 introduces a new challenge, the numeric injection. We have 2 separate input fields here, the login count and the user ID, but the application warns us that only one of them is vulnerable. Start by mapping the application's normal functionality. Enter a valid number into both fields and submit them to confirm the baseline behavior. To find the vulnerability, we need to see how the system handles bad data. We will intentionally inject a broken SQL payload into each field, one at a time, and analyze the response. Looking at this flowchart, we can see the difference in how the application routes our bad data. The login field rejects the input immediately, hitting a solid validation wall. But the user ID field passes the bad data straight to the backend, triggering a flashing red warning node that reads, Database Error. That error message is a highly valuable intelligence asset. It proves our input bypassed the application's initial filters and interacted directly with the database's internal logic. Since we are attacking a numeric field, our final payload drops the quotation marks. We simply enter the number 1, followed by or 1 equals 1 into the user ID box. By omitting the single quotes, the numeric payload resolves successfully within the query, and the database outputs the entire user record set to the screen. The underlying logic remains the same, but the formatting adapts to the environment. Identifying whether a field expects string or numeric data tells you exactly how to structure your breach. In minutes, we manipulated internal access controls through DCL, extracted hidden tables using string manipulation, and bypassed authentication with a numeric payload. None of these exploits relied on brute force. They succeeded because the application systematically failed to properly sanitize user inputs before querying the database. As you continue testing these payloads, ensure you are only doing so strictly within your secure, locally hosted webgoat sandbox environment. Securing a system starts with knowing exactly how to break it. By practicing these injection techniques, you build the analytical skills required to audit and lock down vulnerable applications.